Hi guys, it's Miss Maneely, and I'm going to go over the Quarter 2 review guide to help prepare you for your assessment next week. The assessment is going to cover everything from Units 2 and 3, so that would be everything we did with sampling and experimentation in addition to everything we did with probability and random variables. So I think it covers chapters 4 through 6 in the textbook. So the first problem on the review guide, and I think I set it up so everything's in order that we learned it, but the first question has to do with a Maryland Youth Tobacco and Risks Behavior Survey. This is something we actually did at the high schools in December. It's a collaborative effort between the Maryland Department of Health and Mental Hygiene and the Maryland State Department of Education. The survey results provide data on health-related behaviors of youth in grades 6 through 12. On December 16, 2006, a sample of students at Southern High School completed the survey. The sample of students was chosen using the following procedure. A random sample of 10 teachers with 2A classes was selected, and all students in those classes completed the survey. What sampling design was used to select the students to complete the survey? In this case, because the population was split into groups, and this would be teachers with 2A classes, and a random sample of those classes was selected and included all of the students in those classes, it is considered a cluster sample. If I had split everybody into 2A classes and selected a sample from each class, that would have then been a stratified random sample. If I had just taken a list of all the students that were in a 2A class and taken a random sample of them, that would be a simple random sample. And if I had used some sort of a rule, like every 5th student or every 10th student, then it would become a systematic random sample. In number 2, it says the university's financial aid office wants to know how much students earn over the summer from summer employment. This information will be used to set the level of financial aid, and the population consists of the 3,478 students who have completed at least 1 year of study but have not yet graduated. A questionnaire was sent to a simple random sample of 100 students who utilized the university's Career Center to obtain summer employment, and 39 students returned the questionnaire. So there's 2 types of bias that you're being asked about here. The first has to do with undercoverage. And I think most people can recognize that if they're only questioning or only sending surveys to students who used the Career Center, then there's bias. This is undercoverage. But you want to make sure that you describe where the bias is. Like what's wrong with just questioning students that utilize the Career Center? It means basically that the students who didn't use the Career Center to find summer employment were not given an opportunity to participate. And the reason that creates bias is because the amount of money that these students earned for summer employment could be different from the amount of money that students earned by using the Career Center to find their job. So that's where the bias is present. If the students that responded are different than the students who weren't given the opportunity to respond, then that creates bias. In letter B, now we're looking at the impact of non-response. We only had 39% of our sample respond to the survey. So if it's representative of all of the population of students who had summer employment, then that's fine. But the potential for bias is that if there's something different about the 39 students who responded, or if the 61% of the students who didn't respond earned different amounts of money over the summer, then we're going to get information that doesn't represent the whole population. And so therefore that's the bias. So we're looking at the difference between who responded and who didn't, or who responded and who wasn't given a chance to respond. And that's where we're talking about in letters A and B for number 2. Number 3, it says a large restaurant chain wants to test the market for a new menu item, a grilled chicken sandwich with chipotle salsa. They are interested in both how to market the item and the right price to charge for it. They decide to offer the sandwich at a random sample of 60 different restaurants in the chain using 2 different descriptions on the menu. Half of the restaurant menus were randomly assigned to emphasize healthy eating, and the other half will emphasize the value. Furthermore, each group of restaurants will be randomly assigned to charge either a high, medium, or low price for the sandwich. After a month, they will measure and compare the proportion of customers at each restaurant who order the new sandwich. So suppose the company plans to conduct a completely randomized design. We want to list the experimental units, the factors, and the levels in this experimental design. So the experimental units are the things that receive the treatment. So even though the people are the ones that are buying the food, it's the restaurants themselves that are receiving the treatment. So 60 restaurants would be our units. The factors would be the 2 different descriptions. So the description on the menu is one of the factors, and then the other factor is the price. And actually, I think I'm underlining the wrong thing. So how to market is one of them, and then the price is the other factor. And you can explain this in different ways. I think I wrote the menu description and the price. And then the levels then are going to correspond to each of the factors. For the menu description, we have 2 levels. Either healthy eating is going to be emphasized or the value will be emphasized. And then for the price, we have 3 different levels, either high, medium, or low. And so if I'm talking about an experiment, there's actually going to be 6 treatments. So it's going to be a combination of healthy eating and high price, healthy eating and medium price, healthy eating and low price, and then we'd have the emphasis on value versus high price, value versus medium price, and value versus low price. You were not asked in this problem to list the treatment combinations, but if you were, then you'd want to list all the combinations of factors and levels. In letter B, it's asking what the response variable is. What am I measuring at the end of this experiment? And that tells you very easily it's the proportion of customers at each restaurant who order the new sandwich. Okay? This is a major assessment that you guys are taking, so don't cut corners. Make sure you spell everything out completely and clearly. In the next section, we're actually going to change the scenario a little bit. It says, suppose that 30 of the restaurants in the study are freestanding buildings and that the other 30 are located inside malls. The company suspects that the different building types may actually impact how people respond to the advertising campaign and the price. So the confounding variable in this situation is what might alter the results of the study, or what might create some extra variability that we want to control. And so in this case, it would be the location of the restaurant, whether it's freestanding or inside the mall. Because we anticipate that people will respond differently, this is an opportunity to use blocking in our experimental design. So we only block when we anticipate that there's going to be a difference in those responses. So using a randomized block design is going to be more appropriate. We block according to the location, so there's no randomness there. Either the restaurant's inside a mall or it's freestanding. And then from there, I already have separated my restaurants into 2 groups. From there, I'm going to be running parallel experiments. So all of the restaurants that are inside the mall are going to be randomly assigned to one of 6 of the treatment combinations, and the 30 restaurants that are freestanding will also be randomly assigned to one of the 6 treatments. In letter E, it says, can the restaurant chain generalize the results of the study to other restaurants in its chain? The only way that we can generalize to a larger population is if we've used random selection. And if we go back into the problem, it says that they used a random sample of 60 restaurants in their chain. So because we've chosen the restaurants randomly, I can generalize my results to the rest of the restaurants in the chain. The second part of that question asks, can the chain conclude causation if there is a difference in the proportion of customers who order the new sandwich? And in this case, since we had random assignment to each of the treatment combinations, if there is in fact a difference, I can conclude causation. So those are the 2 inference questions that we ask, and they both have to do with randomization. So if my subjects have been randomly selected from the population, I can generalize my conclusions to the larger population. If my subjects have been randomly assigned to treatment groups, then I can also generalize and make inferences about cause and effect. All right, so that takes care of the second unit on sampling and experimentation. The next questions all deal with probability. So in number 4, it says among guests at a wedding, 34% are friends of the groom, 42% are friends of the bride, and 60% are friends with either the bride or the groom. The remaining guests are family members or friends of the couple's parents. So let's make sure we understand the information that we're given. I'm going to use B for bride and G for groom. Okay, so the probability that they were friends with the bride is 0.42. The probability that they are friends of the groom is, let's see, did I do this right? Yeah, 0.35, or 34, sorry. And then the last statement says that probability that they're friends with either the bride or the groom. So that's the next piece of information, bride or groom. And that is 60%. Okay, so if I'm trying to do a Venn diagram, make sure that you have your population or your sample space identified with the rectangle. I'm going to go ahead and put my bride here, my groom here. Now normally we start with the overlap, and that would be the probability that a guest is a friend of both the bride and the groom. But I'm not given that information in the problem, so I have to figure it out. Well, if I take a look at all the information I'm given, I can actually relate that using one of my probability rules. I know that the probability of either the bride or the groom is going to be equal to the probability of the bride plus the probability of the groom minus the probability of both. And that's what I'm interested in finding. That's my unknown. But I have all the other pieces, so let's fill them in. The probability of either is 0.6, of just the bride is 0.42, just the groom is 0.34, and let's just call this x. Well, if I solve for x, I'm basically just going to find the sum of 0.42 and 34 and subtract it from 0.6, and I'm going to end up with a negative 0.16. But if I solve this equation, I'm going to have the probability of bride and groom is equal to 0.16. And so this in here is going to be 0.16. If I know that the total for my bride event is 42%, then I just need to subtract the 16 from the 42. And actually, let me do this on the calculator so you can see the math that I'm actually doing. Okay, so let's go back so you can see where I came up with that 16%. The 0.42 plus the 0.34 ends up being 76%. So basically we have 0.6 is equal to 0.76 minus x. So if I solve for x, if I subtract 0.76 from both sides, I'm going to get a negative 0.16, and that's going to equal a negative x. So negative 0.16 is equal to a negative x. And if I divide through by negative 1, I get the 0.16. So now if I'm going back to my Venn diagram, I know that the probability of a person being a friend of the bride, we said that's 42%. So I want to take that 42% and subtract the overlap. And I get 0.26. I'm going to do the same thing with the groom. I know the probability that someone came there to visit the groom is 34%. If I take away the 16%, that leaves me with 0.18. And then if I add those values up and subtract from 1, that gives me the probability that they were there for neither the bride or the groom, and that would be 40%. And that makes sense that it's the complement of that 60%. So there is your completed Venn diagram. It also turns out that we've already answered the question in Part B. If a wedding guest is selected at random, what is the probability that the guest is a friend of both the bride and groom? So we actually answered that up there. Okay, and number 5. This one is actually a little bit more complicated. I'm actually going to open up my... maybe not. Nah, I'm going to keep it. Okay, so in this situation, we've got 2 spinners. A game involves spinning each of the spinners below and taking the sum of the numbers selected. And you're asked to come up with a probability distribution. Remember, the probability distribution lists all the outcomes along with their probabilities. So if I think about it, if I'm adding the numbers on the spinners, the lowest sum that I would have would be 2. That's going to be my lowest. And since the most I can get on either spinner is 4, the highest sum I could get would be 8. And so I'd have all the values in between. All right, so I now need to figure out the probability of getting each of these values. Well, if I think about it, there's only one way that I can get a sum of 2. But there are multiple ways I can have a sum of 4, right? I could get a 2 and a 2, a 1 and a 3, a 3 and a 1. All of those would add up to give me 4. If I'm thinking about the total number of outcomes, though, I've got 4 outcomes on the spinner and 4 outcomes on the spinner. That means that there are 16 outcomes total. And so I need to think about the number of ways that I can get each of these sums. But they're all going to be divided by 16. So if I think about how many ways I can get 2 as my sum, there's only one way, and that would be if I got a 1 each time. So only one of my outcomes out of the 16 would give me a 2. But let's think about all the ways I can get a 3. I could do 1 and 2. So I could get a 1 on the first spinner and a 2 on the second, or I could get a 2 and a 1. So in this case, there are 2 outcomes that would add up to 3, and 2 out of 16 would be the probability. So now I'm looking at a sum of 4. Well, if I think about a 4, I could have a 1 and a 3, a 2 and a 2, oops, or a 3 and a 1. Those are the 3 ways that I could get a sum of 4. And so that's going to be 3 out of my 16 outcomes. For a 5, I could get a 1 and a 4. I could get a 2 and a 3. I could get a 3 and a 2. Or I could get a 4 and a 1. So in this case, there are 4 ways. With a 6, I can't do 1 and 5. That's not going to give me a 6 because there is no outcome of a 5. So I can do 2 and 4. I can do 3 and 3. Or I can do 4 and 2. So again, we have 3 ways. And you might start to see a pattern. There are only 2 ways to get a 7. Either I have a 3 and a 4 or a 4 and a 3. And with an 8, there's only 1 way that can happen. That would be a 4 and a 4. So that's how I would construct the probability distribution for this scenario. It does take a little bit of time. If I want to compute or calculate the probability that x is greater than or equal to 4, now many of us have been doing the binomial and geometric distributions. Be careful that you don't confuse what we've learned about those random variables with this particular random variable. The random variable x in this case has this probability distribution. It is not geometric. It is not binomial. It is not normal. So I have to use the probabilities that I've listed. And so if I want to determine the probability that x is greater than or equal to 4, I'm taking the probability that x equals. In fact, let me go ahead and just put a check mark on top of all of the different outcomes it could be. It could be a 4, a 5, a 6, a 7, or an 8. So I need to add up all those probabilities. And when I do, so I'm going to have 3/16 plus 4/16. And obviously you're going to do this on your calculator. And when you add that all up, we have 13/16. And you can either leave it as a fraction or write it as a percent or a decimal. If I want to know the probability that the sum is an even number, so what does that mean if the sum is even? If I want to express this as a random variable, that means it's the probability that x is, let's see, 2, or x is 4, or x is 6, or x is 8. And just like before, each of these are considered disjoint, so I can simply add the probabilities together. So that's going to be 1/16 plus 3/16 plus 3/16 plus 1/16. And so that's going to end up being 8/16 or simply 1/2. And you may have actually been able to figure that out. The probability of getting an even number, we should get an even number, an even sum half the time, given the outcomes that we already had. So in number or letter D, it says, what's the probability that the sum is 6 given that the sum is an even number? So the probability that the sum is 6 given that it's even. Okay, so here's now where we have to use one of our probability formulas or our probability rules. If I'm dealing with a conditional probability, I'm going to look at the probability of both 6 and even. And I'm going to divide by the probability of my given or condition. All right, so for the sum to be both 6 and even, there's really only one outcome that is both, and that would be if I landed on 6, because it has to be both. So the probability on the top is going to be 3/16. The probability of getting an even number is going to be 1/2, or actually it might be easier if I look at it as 8/16. I already found that probability. And when I divide, those 16ths are going to cancel, and I'm going to end up with 3/8, or 0.375. And the last question is asking you to find the expected value of x. There are a couple different ways of doing this. I'm going to go ahead and work it all the way out. The expected value of x is determined by taking the outcome times its probability and adding them up. So I'd have 2 times 1/16 plus 3 times 2/16 plus 4 times 3/16. And this is tedious. But if we do it out by hand using the formula, the expected sum is going to be 5. You can also use your calculator where you enter in the outcomes into list 1 and the probabilities into list 2. And I will show you in case you don't remember how to do this. I'm not sure what I have in my lists, but I'll just use the data that I have in there. If you want to find the expected value, go to Stat, Calc, and then use your one variable statistics command. Now, even though I have 2 lists, it's still one variable. The variable of interest is going to be the sum. So I'm going to go ahead and enter list 1 for my sum. But I also have probabilities that are listed in list 2, and those are my frequencies, or in this case, they're my relative frequencies. So I'm going to use list 1 and list 2 to determine I can get everything. I can get my mean, I can get my standard deviation, I can even get a 5-number summary. So if I go back, my mean is going to be x bar, which is 1.111. Obviously, this is different data. Sorry, I was confusing myself for a second. The standard deviation is going to be the sigma of x. Okay, so sorry. Yeah, the data on the calculator is different than the data that we're using in this problem, so that's why the numbers are different. Okay, let's take a look at number 6. Taylor passes through 2 traffic lights on her way to school each morning. The lights are connected through a system of sensors and do not operate independently. The probability that Taylor makes it through the first light without stopping is 68%. If she makes it through the first light without stopping, the chances she'll also make it through the second light without stopping is 75%. However, if she has to stop at the first light, the likelihood of making it through the second light without stopping is only 22%. Assume Taylor will only pass through an intersection without stopping if the light is green. The first thing you're asked to do here is construct a tree diagram. So the first thing we want to talk about, or the first set of branches, is going to be the first light. So we're going to go ahead and say she passes through the first light without stopping. Basically means that the first light is green. So the first light is either green or not green. I'm not going to worry about all of the different, red or orange or yellow or whatever. It's either green or not green. And the probability that she's able to pass through the first light without stopping is 68%. That means that 30% of the time, or I'm sorry, 32% of the time, it is not green and she's going to have to stop. Well, she passes through a second light, so I need a second set of branches. And she's either going to pass straight through, which means the light is either green or it's not green. Let me use the same notation. Okay, and so it says if she makes it through the first light without stopping, the chances she'll also make it through the second light without stopping is 75%. So there's a 75% the second light is also green if the first one was, and there's a 25% chance that it won't be. However, if she has to stop at the first light, the chances of making it through the second light without stopping is now only 22%. So there's only a 22% chance that the second light is green, and that would make this a 78% chance that it's not green. Okay, so that sets up the situation. In letter B, it says that you're defining the random variable g to represent the number of green lights she encounters on her way to school each morning. And you're asked to complete a probability distribution for g. So what I'm going to do on my tree diagram is I'm going to list the outcome in terms of the random variable g. So if g counts the number of green lights, I'm going to say for this first path, where she gets a green light and then another green light, that g is 2. The second path, let me do this in a different color. So the second path would be this situation here where it's green and then not green. That means that the number of green lights she had was only 1. In the third path, it's not green and then green. So that would be another one where g is only 1. And then in this last path, it was not green and then not green. So the value of G, or the number of green lights, would be 0. So once you have your tree diagram, you can easily find the probabilities. If I wanted to find the probability, in this case, of having this outcome, which would be 2 green lights, I'm just going to multiply 0.68 times 0.75. And then I can do the same thing for each of the branches. So if you go down to letter B for your probability distribution, the probability that G is 0, so it's this outcome here, is going to be 0.32 times 0.78. And that's going to end up giving you 0.2496. There are 2 ways that she can hit 1 green light, so I have to multiply along the branches and then add the branches together. So it's going to be 0.68 times 0.25 plus 0.32 times 0.22. And that should give you a probability of 0.2404. In the last one, the probability that it's going to be 2 green lights is just going to be 0.68 times 0.75, and that is going to happen 51% of the time. Okay, be prepared for a problem like this, but expect that you may not be prompted to come up with a tree diagram first. So you have to be able to go from the original setting or the original prompt straight into the probability distribution. So sometimes you might have to construct a Venn diagram, sometimes you might have to construct a tree diagram to truly understand the situation before coming up with a probability distribution. Okay, let's take a look at number 7. Many employers require prospective employees to take a drug test. A positive result on this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees actually use drugs. The false positive rate is 5%, and the false negative rate is 10%. Construct a tree diagram. We're always going to start with the truth about the population. Either they use or they don't use. And we're told in this case that 4% of the population, or the 4% of the prospective employees do use. That means 96% do not. So then, whether or not they use, they're either going to test positive or negative on this drug test. So a false positive would be basically that I get a positive result from someone who doesn't use. And so this would be the branch indicating a false positive. And so I know that's going to occur 5% of the time. 95% of the time, I'm going to get the correct negative result that I should get. A false negative means that I'm getting a negative result from someone who uses, and that's going to be this group of people here. And the false negative rate is 10%. That means that 90% of the people that use are actually going to test positive. So question B says, what is the probability that a prospective employee will test positive? So the probability of testing positive, notice that there are 2 paths that I can take to get to that positive result. I can either have someone who uses and tests positive. So again, the and, I'm going to multiply 0.04 times 0.9. Or I could find somebody who doesn't use who also tests positive incorrectly. So that would be 0.96 times 0.05. And when you multiply that all out, you get 0.084. Remember, though, that this path here that I'm looking at, this use and test positive, this probability right here is not an and. This probability corresponds to the probability of testing positive given that the person uses. So be careful, because a lot of times when people see the word and, like use and test positive, they automatically think that they can multiply all their probabilities together. In this case, the reason they can multiply is because it follows the formula. So the probability of A and B is equal to the probability of A times the probability of B given A. A lot of people forget that second part and just think that they can always multiply probabilities. In letter C, it says, suppose that an employer has 20 prospective employees. What is the probability that at least one will test positive for drugs? At least one. So the probability, I always write this out, of at least 1 in 20 test positive. Okay, so what that means is it could be 1, it could be 2 people test positive, it could be 3, or it could be 4, or it could be 5, or it could be 6, or it could be 7. All those ors I'd have to add together, and that would take a long time. So instead, I'm going to look at the complement. The complement of at least 1 would be none. So I'm looking at the probability, or 1 minus the probability that none in 20 test positive. Well, if nobody tests positive, that is the same thing as 1 minus the probability that they all test negative. So I've got to figure out the probability of testing negative. Well, if I know the probability of testing positive is 0.084, I got that in number 1, then the probability of a negative result is just going to be 1 minus that, which is 0.916. That's the probability I'm going to use down here. So it's going to be 1 minus, well, if all 20 people test positive, that means the first person tested positive, and the second one tested positive, and the third one tested positive, and the fourth one, and the fifth one, and the sixth one. So with and, I multiply. And if we assume that we have independence between the different employees, then I can multiply all those probabilities together. So that would be like doing 0.916 times itself 20 times, or simply taking 0.916 to the 20th power. And when you do that, you should get 0.8271. So there's almost an 83% chance that this employer is going to have a potential employee test positive for drugs. All right, and then the last question in this says, suppose a prospective employee tests positive for drugs. That is now given information. I know they test positive. Then I'm trying to find what's the probability that they actually use. So the probability, if I know they test positive, what is the probability that they actually use? So remember, the given information always goes here. If I think about my formula, the probability, if I'm dealing with a conditional probability, it's going to be the probability of both, they use drugs and test positive, over the probability of the given. So I'm going to have to rely back on my tree diagram again to find the probability that they use and test positive, and that's this first branch, which is going to be 0.04 times 0.9. over the probability that they tested positive. Well, again, I found that already. That was 0.084. And if we divide, we should get 0.429. So only about 43% of the people that test positive are actually going to be using drugs. So this test actually doesn't seem very reliable in this case. Okay, number 8. We're going to jump to just combining or combinations and transformations of random variables. You're given a table with a bunch of different operations. So this is taken out of context. So just be prepared on the quarterly assessment that there'll be some sort of context associated with your random variables. We've seen a lot of examples with like bowling or heights of men and women, and you're given the mean and standard deviation of each. So just know that you're going to be given a context and you'll be applying these rules to be able to answer some of the questions. So we're told that a random variable A, and I like to have a little table. So I'm going to have my random variable A and my random variable B. I'm going to come up with my mean and my standard deviation. So the random variable A, we're told, has a mean of 16 and a standard deviation of 6. And my random variable B has a mean of 22 and a standard deviation of 3. Now, the one thing I also am going to remember is that all of my formulas, especially the ones that deal with a combination of random variables, rely on the variance. So I'm also going to go ahead and find the variance for each of my random variables, which is just going to be the standard deviation squared. Okay. And when you're just dealing with a transformation like multiplying or adding a single value or a single number, you don't actually need to use the variance. You can just deal with the standard deviation alone. But as soon as you're adding two random variables together or subtracting two random variables together, you must work through the variance to come up with the standard deviation. So for example, in the first one where I've got 2a plus 5, whatever it's telling me to do to the random variable, I'm going to do to the mean. So that means I'm going to take 2 times the mean of a, which is 16, and add 5. So 32 plus 5 gives me a new mean of 37. When I'm dealing with a standard deviation, this is an example where technically you don't need to use the variance. I would just take 2 times the standard deviation of a, which is 6, but I got to remember that adding or subtracting a number to a set of values is not going to change the spread. So I'm not going to worry about adding a 5. The new standard deviation would be 12. If you prefer to work with the variance, which is really the proper thing to do, then we would simply do 2 squared times the variance and then take the square root. And what you'll find is it's the same as 2 times 6, and you'll get 12. The next one is 50 minus b. So again, I'm going to do whatever it tells me to do. I'm going to do that to the mean. So it's going to be 50 minus the mean of b, which is 22. And that gives me 28. When it comes to dealing with the standard deviation, though, the 50 is not going to change my standard deviation, and I'm never subtracting. So it doesn't matter that I'm subtracting my random variable from 50 or whether I subtract 50 from my random variable. My standard deviation doesn't change. It's going to remain 3. And the next one, now I'm required, because I'm dealing with a and b and I'm combining them, I have to work with my variance. So to find the mean, I'm just going to take the mean of a, 3 times the mean of a, plus 2 times the mean of b, which is 22. And when I perform that operation, I get 92. To get to the standard deviation, though, I have to deal with the variance first. So I'm doing 3 squared times the variance of a, which is 36, plus 2 squared times the variance of b, which is 9. And the standard deviation is the square root of all that. And you can do it in 2 steps if you want, but this ends up giving you 18.974. In the next one, we have a minus 3b. So I'm going to do that to my mean. 16 minus 3 times the mean of b, which is 22, and I get a negative 50. Don't freak out if your mean is negative. It's okay. When I'm doing the standard deviation, though, again, I have to work with the variance. So I'm going to take the variance of a, which is 36. I always add, so I will never, ever, ever be making my variance smaller unless I'm dividing. So that minus is still going to stay, or is going to become a plus, and then I'm going to have 3 squared times the variance of b, which is 9. And to calculate the standard deviation, I take the square root of that whole quantity. And that gives me 10.817. The last one is an important characteristic about random variables. If I'm adding a plus a plus a, that is not the same as 3a. It's not really going to make a big deal, a major difference with a mean, but it does change the standard deviation if you misinterpret that. So in context, you might see that like test scores are being doubled or tripled. And in that case, you want to multiply by 2 or 3. But if I'm talking about adding several things together, like I'm looking at tests from 2 different classes that happen to have the same distribution, I have to look at it as x plus x or a plus a and not as 2a. Okay, so to calculate the mean, I'm just going to add 16 plus 16 plus 16, which obviously is the same as 3 times 16. It doesn't change anything. But my mean of a plus a plus a is going to be 48. It does affect the standard deviation, though, because, again, I have to add the variances. So I'm going to be adding the variance of a plus the variance of a plus the variance of a and taking the square root of that. And that's going to give me, oops, I added the wrong variances. These should be 36s, not 9s. Let me do it this way. I'm sorry, the variance of a is 36, and then I'm going to take the square root. And that's going to end up giving me 10.392. So if you think about what I did in that last one, the variance, or the standard deviation, I'm taking the square root of 6 squared plus 6 squared plus 6 squared, which is ultimately 3 times 6 squared, and the square root of that. If I had looked at this as 3 times a, what I would have for my standard deviation would be 3 squared times 6 squared, and the square root of that. So notice I have an extra factor of 3. So it does matter. A plus A is not the same as 3a. And there is a problem like that on the test, so make sure that you understand that distinction. Okay. In number 9, it says a game at a local fair involves tossing a 6-sided number cube. Each face on the die represents the amount won. 3 of the sides display $0, 2 sides display $1, and 1 side displays $5. It costs $2 to play the game and toss the die. So W represents the net profit, and that would be the income from the game minus the payout to toss the die one at a time. So complete the table for the probability distribution of W. So if I am, let's see, so we've got the two outcomes. We can earn $0, $1, or $5, and it costs $2 to play. And we're talking about the profit. So if someone lands on 0, that means as the company or the game, they get to keep that $2 profit. So this winning of $2 corresponds to the $0 outcome on the die. And that can happen 3 out of 6 times, or 1/2, or 0.5. 2 sides display $1. Well, if I'm paying $2 to play, even if I have to pay out $1, my profit is still $1. And so this is going to occur 2 times out of 6. Actually, let me keep it as a fraction. Oops. And the probability of losing $3 would happen if someone lands on the $5, because they'd have to pay the $5 and they'd only be gaining 2, so that would be a loss of $3. And there's only one way that that can happen. If we want to determine the mean and the standard deviation, we can easily do this using our calculator. Let me find my calculator. There we go. So basically what I'd want to do in my lists is list all my outcomes. So I have an outcome of $2. Make sure you put these in the correct order. And then the probabilities. So 3/6, 2/6, and 1/6. Okay, I recommend putting them in your calculator as fractions and letting your calculator do the division, because even though you're seeing a rounded value, your calculator is maintaining all of those decimal places. And this way, when you calculate your mean and your standard deviation, you won't have any rounding errors. So I'm going to go back to my home screen and use my stat calc one variable statistics command. And again, you want to make sure that you not only include the outcomes that are in list 1, but the probabilities that are in list 2, because those represent your relative frequencies. And so X bar is going to correspond to the mean. So the mean of W in this case, sorry, it keeps disappearing, was about 83 cents. And the standard deviation of W, and let me just show you again on the calculator. You want to make sure that you use the standard deviation, the sigma sub X, which is 1.772. And again, we're dealing with money, so make sure you use appropriate units. So those are the mean and the standard deviation for W. In letter C, it says the fair owner pays an attendant $60 to run the dice game each day. What's the minimum number of games that must be played for the expected value of the net profit, which is what we have here, to cover the cost of the attendant's salary? Well, if I'm expecting to make about 83 cents per game, and I need to raise 60 bucks, all I need to do is take that $60 and divide it by the expected winnings. And so if I take 60 and divide it by the 0.833, I get 72.028. Now this is going to be This is a rounded value. In fact, if you were to calculate the probability exactly, this number is exactly 72. And 72 games will actually help you break even, will help you break even. If you do happen to get a decimal like you do here, you always want to round up. So it would be more appropriate to say 73 games because you need at least 73 games to break even. In this case, though, 72 is the actual answer, but based on the rounding error here, you'd want to say 73 games. You'd always want to round up. Okay. In number 10, it says a certain slot machine earns a casino a mean income of $260 per day, and the standard deviation is $79. Suppose the slot machine operates every day, 365 days per year, and the income each day is independent of the next. Let the random variable t represent the total income from the slot machines for the entire year. Determine the mean and the standard deviation. Again, I am not going to use 365 times my random variable. I have to think of it as, so t is not equal to 365 times x. It would be equal to x plus x plus x plus x. So if x is the daily income, t is going to be x on the first day plus x on the second day plus x on the third day, all the way up to x on the 365th day. So this is one where you have to be careful. It's not going to be 365 times x. So the mean of t, and the mean of t isn't going to matter. I'm basically going to add 260 plus 260 plus 260 365 times. So the mean will end up being the mean does end up being 365 times 260. So that is true. And that will end up giving you a mean income for the year of $94,900. To find the standard deviation, we have to work with the variance. And that's going to be the variance plus the variance plus the variance. And the variance was $79. So it would be the variance squared plus the variance squared plus dot, 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 the variance squared. And it would be 365 times the variance squared. It would not be 365 squared times the variance. Or times the, yeah. So if I want to find the standard deviation, I'm taking the square root of that quantity. And I get $1,509.29. So now I know the mean and the standard deviation. Letter B says, if the random variable t from part A follows an approximately normal distribution, what is the probability that the slot machine will earn a total yearly income of over $95,000? So now I'm looking for the probability that t is greater than or equal to 95,000. You want to make sure that you standardize it. So to find z, I'm going to take my outcome, 95,000. I'm going to subtract my mean of 94,900, and I'm going to divide by my standard deviation of 1509.29. And that calculation will give you a z value of 0.066. And on your calculator, just to practice, we're going to go to normal CDF. Now with a normal function, you have to enter your low bound and then your high bound and then your parameters. This is different than the commands for the geometric and the binomial distribution, which require you to enter the parameters first. So the lower bound in this case, since I'm dealing with a greater than, I'm going to go ahead and enter the values for t. So 95,000. My upper bound would be a huge number, so I'm just going to type in 999999999. You could also do like 1 times e 99, and that would give you a large upper bound, because I can't type infinity into the calculator. Since I'm dealing with my random variable t, I want to make sure that I'm entering in the mean and the standard deviation of t. So that's going to be 94,900 for my mean, and my standard deviation is 1509.29. And that gives me a probability of 47.36%. Okay. You could also have done the same thing using Z, except your mean and standard deviation would be 0 and 1. Okay, almost done, guys. Number 11, it says a youth basketball coach instructs each of the players on his team to attempt a free throw shot. The team consists of 12 players of varying ability levels. Each player gets one shot, and shots are independent of each other. If the probability of making a free throw is known for each player, could a binomial distribution be used to determine the probability that at least 10 of the players make their shots? So let's think about the conditions for a binomial. I need to have two outcomes, success and failure. So if we define a success to equal a make, that condition is held. Okay. It also tells me in the problem, independence. Independence is stated. So that condition is met. Okay. It says if the probability of success is known, so let's say P is known, but it says it's known for each player. And we're also told that the players have varying ability levels. So what that tells me is that while the probability of success for each player may be known, it's not constant. Because it's going to depend on the ability level of the player. And so for that reason, the distribution is not binomial. Okay, I do have a fixed number of trials. In this case, we're looking at 12 players. Now, if this statement wasn't there, so if that statement of varying ability levels was not there, then what I could say here is while if P is known for each player, we would have to make the assumption that it is constant. So if the statement was not in the problem that tells me that the ability levels of the players is different, then I could assume that P is constant. And then if I can assume that, I could go ahead and say that the distribution is binomial. But you'd want to state the assumption that P is constant. All right, and number 12. Do people have a preference for the last thing they taste? Researchers at the University of Michigan designed a study to find out. The researchers gave 22 students 5 different Hershey's Kisses, milk chocolate, dark chocolate, cream, caramel, and almond, in random order, and asked the student to rate each one. Participants were not told how many kisses they would be tasting. However, when the 5th and final kiss was presented, participants were told that that would be their last one. Of the 22 students, 14 of them gave the final kiss as the highest rating. So assume the participants in the study don't have a special preference for the last thing they taste. That is, assume the probability a person would prefer the last kiss, regardless of what it was, would be 20%. We can assume independence here between the people. What is the probability that exactly 5 of the 22 participants would prefer the last kiss they taste? I have to identify what my random variable is and what setting I'm dealing with and what probability distribution I'm going to use. So it's really important that we identify that we are looking at the number. So if I say that X represents the number who prefer the last kiss, and then I want to talk about how X is distributed. Since we've got a fixed number of outcomes, we've got 22 people, we've got a fixed probability that's constant. The only other thing I have to assume is independence. So I can say that X is binomial with an n value of 22 and a probability of success of 0.2, assuming independence. So I have to state that if I'm going to call this distribution binomial, because I don't believe it tells me that in the problem. So in letter A, it says, what's the probability that exactly 5 of the 22 participants would prefer the last kiss they tried? So I'm looking for the probability that X equals 5. On the calculator, I would use the PDF command. So I'm going to go to my distribution menu. It's easier if you scroll back and you want to select the binomial PDF. we always enter in, for binomials and geometrics, we enter the parameters first. So n is 22, p is 0.2, and n in this case, or x, I'm sorry, is 5. So we're looking for 5 successes in n trials. And that gives me 0.18. Since the 9.7, that's going to actually round up to 0.19. If you wanted to do this by hand or use the formula, I'd be looking at this binomial coefficient would be n choose k, which in this case would be 22 choose 5, times the probability of success, which is 0.2, raised to the number of successes, which is 5. Then I'd want to multiply that by the probability of failure, which would be 0.8, to the number of failures. Well, if I have 22 total and 5 of them are successes, that must mean that the other 17 are failures. And if you perform this operation, you would get the same thing. And to calculate that 22 choose 5, I'll show you how to do that as well. You can do that on your calculator. Put the 22 in first, then go to math, probability. I always scroll back, it's faster. And then you would choose your NCR command. And that gives you the number of combinations, or the number of ways that we can have 5 successes in 22 outcomes. The calculator uses the variable r instead of k, but it's the same thing. And so if I take that number times 0.2 to the 5th, and then I multiply that times 0.8 to the 17th, I will still get the same answer that I got using the calculator's PDF command, which is a lot faster. Make sure, though, if you're going to be using the PDF and CDF commands, that you define your variable and tell us how it's distributed. In letter B, what's the probability that 14 or more of the 22 participants would prefer the last kiss they tried? So now I'm looking at the probability that x is greater than or equal to 14. So I know if I have an inequality that I have to use the CDF command. So this is just to kind of keep in mind, the PDF command corresponds to equals. The CDF command, however, only corresponds to less than or equal to. So if that's not what I'm given in my problem, I have to transform the expression. So let's take a look at the complement. At least 14, the complement would be less than 14. So that would be 1 minus the probability that x is less than 14. I'm going to keep the boundary, flip the inequality. Since it started with an equals, the complement will not include the 14. But that still doesn't give me the inequality that I need to be able to use the CDF command. So I'm going to scoot down one more notch, and that's going to be the probability that x is less than or equal to 13. And so now when I go to my calculator, I'm going to choose the binomial CDF command. I still enter in my parameters first. So 22 is the value of n. The probability of success is 0.2. And I'm going to include my upper bound, which is 13. And remember, with binomial and geometric, that equal sign makes a difference. It doesn't make a difference when you're dealing with a normal distribution. And I forgot to do the 1 minus. So basically, I'm going to be doing 1 minus, what did that say it was, 0.99999? And so on the calculator, I can simply do 1 minus, and then do second answer. And so you're going to get a very, very, very small number. And that's just scientific notation. 1.01 times 10 to the negative 5. That's what that e negative 5 means. It's about 0. And so obviously it's really, really unlikely to have a situation where you have 22 people, you do this experiment with them, and 14 of them prefer the last kiss. The chances of that happening just by chance alone, the likelihood of that being just a coincidence, is almost 0. It's very, very, very unlikely for that to happen by chance alone. So the last question is an inference question. It's not on your quarterly assessment, but it does kind of lead us into what we're going to be doing all of second semester. It says, based on the probability that you found in part B, would you conclude that people, in fact, do prefer the last thing they taste? Well, if it was just a coincidence, then I would expect the probability of 14 or more people choosing the last kiss to be pretty high if it was just coincidence. The fact that the probability is really small, that tells me that it's not chance but happening, that people do in fact tend to prefer the last thing they taste. And so what I would say, basically, I'm just going to read this instead of type it. Since the likelihood of at least 14 out of 22 people preferring the last kiss is so unlikely, it's less than 1%. And that's less than 1% of the time would that have occurred by chance alone. We have evidence to conclude that people do in fact prefer the last kiss. All right. So good luck. I hope that this was helpful. It was almost exactly an hour long, so I hope that it was beneficial to you. Good luck on your quarter assessment.